Let's take a look at our intro to section 2.6. I want to take a look at some basic algebra here, and I want to talk about what that means for linear analysis and the systems that we're going to be solving. So in a basic algebra course like Algebra 1 or Algebra 2, a linear equation is of the form ax equals b, or if you add b to both sides, ax equals b, where a and b and x are just real numbers. To solve this equation, we multiply both sides of the equation by A inverse, if it exists. And that's the multiplicative inverse for A, that is. A inverse times A, or A times A inverse, should give you 1. That's like 5 1/5, or negative 3 and negative 1/3. And that's true for any A, except for A equals 0. A equals 0 is the only real number that doesn't have an inverse. And so then if we choose to make A not equal to 0, then we have the following: AX equals B, and we can solve using A inverse. It looks a little bit like this. Let's see. We're going to take AX and B, and we'll multiply both sides of the equation by A inverse. And because A times A inverse is equal to 1, we get 1 times x is equal to A inverse times B, or x is equal to A inverse times B, and there is, in this case, one unique solution. And so what we can note here is, if A inverse exists, the equation has one unique solution. So it's just some old school algebra. Now there is the possibility that A does equal 0. So coming down here a little bit, if A does equal 0, then 0x equals b gives rise to two possible cases. And we cannot multiply both sides by A inverse here because A inverse doesn't even exist for A equals 0. So we have to intuitively sort of solve this situation as follows. And we're going to break it up into two cases. A is 0, but B is not 0, like B equals 5. And then we get an equation that looks something like this. X times 0 is equal to 5. And we know that for any value of, or for any real number, 0 times any other number should be 0. And that's not the case here. So no such x exists, and we have no solution. So if A inverse does not exist, the system might have no solution, especially if the other side of the equation is a non-zero constant. So that's our little result here. The other possibility is that both A and B equal 0, and then you get the following equation, which is a little bit different than this one up above. Down here we see 0x equals 0, and now we know that for any number x, it will be true that 0 times that number is equal to 0, and x can be any real value, and now we have infinitely many solutions. So in this case, A inverse does not exist, as well as the case above. The system might also have infinitely many solutions. So we got to be really careful when the inverse in algebra doesn't exist. There's two different possibilities. So let's take a look at these same ideas for our linear class. We're really looking at this macro version of a bunch of linear equations. This is a collection of linear equations. And we can actually treat it the same way. That is to say, case 1, if let's go back here. if A inverse exists, then we have AX equals B, and then we multiply both sides of this equation by A inverse. In this particular case, we have to multiply both sides by A inverse on the left because we're dealing with matrices, and the multiplication won't be defined if we multiply on the right side, and we have to be consistent and make sure our dimensions match up nicely here. Now, what we can then do is reassociate this matrix multiplication as A inverse times A times X in that order. We can't commute, but we can reassociate. And this is just A inverse times B over here. And that's going to give rise to the following. A inverse times A, or A times A inverse, should give rise to not the number 1, but the identity matrix of the appropriate size. So that's the definition. And we're going to talk about that in just a little bit in our next video. I just wanted to sort of give you the analogy between algebra and linear algebra here. This will then be I times X is equal to A inverse B, or the identity matrix times X is always going to give us X, as the identity matrix is the multiplicative identity for matrices. And this is A inverse B. And so it turns out if A inverse B exists, then we can solve for X by doing this product. Now, what I'd like to say about that is, no matter how complicated A inverse is, or whatever the B column is, this product, A inverse times B, that multiplication is only going to yield one result. And so just like above in the regular algebra versus linear algebra, if A inverse exists, the system has one unique solution. So there's our result. And vice versa, if the system has one unique solution, then the A inverse should exist. So maybe I should say, let's see here. Let me delete this and rewrite this statement. This is a bidirectional implication. That is to say, it's a two-way street in terms of the if-then statement. And so what I really should say here is A inverse exists if and only if the system has one unique solution. So that statement goes both directions. If A inverse exists, then the system has one unique solution. And if the system has one unique solution, then A inverse exists. You can't have one without the other. And so that mirrors our first result right here, right? If A inverse exists, the equation has one unique solution. Now, this is a little bit different. A doesn't have to be 0 here, but if A inverse does not exist, then either the system has no solution or infinitely many solutions in terms of mirroring our algebra up above. Now, A doesn't necessarily have to be 0 here for this to be the case, because we're no longer talking about scalars, we're talking about matrices. But in terms of A inverse existing or A inverse not existing, the structure is the same in terms of one solution or the possibility of no or infinitely many solutions. So that's our little introduction to this section.